Okay, we're going to talk about flight instruments today. And talking about flight instruments, the first thing we're going to go ahead and do is talk, okay, the action, describe the operational characteristics, functions, limitations, and selected CH-47 flight instruments. Conditions in a classroom given the CH-47D, the instrument trainer, and the student handouts. Standards, correctly answer in writing without reference 5 of 7 questions pertaining to the operational characteristics, limitations, and functions or malfunctions of the CH-47D flight instruments in accordance with TM 1-1520-240-10 and the student handouts. Safety requirements, none. Risk assessment, low. Environmental conditions, none. And the evaluation for this, each student will be evaluated on the block of instructions during the first written examination. This is a criterion type examination requiring a go on each scoreable unit, or each scored unit, and you will have 90 minutes for the exam. Any questions about that? Okay. Now, you'll notice with the CH-47D, if you look at that instrument panel, there's a lot of instruments. And we could spend 6 hours to 2 days talking about instruments. But the only instruments we're really going to highlight are the ones that are unique to the CH-47D. So you're going to find out as we cover some of them have some similar characteristics to other instruments and other aircraft that you're coming from. But then we're going to key in on the things that make these instruments different for the CH-47. We're going to start off with the horizontal situation indicator. We call it HSI for short. And we have 2 of them. And talking about the HSI, we have a pilot's HSI and we have a co-pilot's HSI. But the one thing you have to keep in mind as we go along is between the pilot and the co-pilots, there are no differences. They do the exact same things. They have the exact same characteristics. Why is that going to be important? Because later on when we talk about one of the functions associated with the HSI, you're going to find out that the system has to know which one do you want those computers to fly off of. And so we have to designate it. How does that help you? By keeping in mind that they're both identical, they both have the same characteristics, so therefore we've got a special button that will designate for the system which one we want the computers to use. And we'll talk more about that as we go along. Okay, there's your pilot's HSI. There's your co-pilot's HSI. And now we're going to get into everything as we go along. Each indicator can display the following. Helicopter present heading. That's no different than any other HSI. Agreed? And I don't care what you're coming from. Frequency modulating homing. Okay, big word for FM homing. We have FM homing capability, but what you're going to find out with some aircrafts that works, some aircrafts that doesn't work, depending on whether or not the FM modulator is installed. Sometimes it works, sometimes they don't. I think most of them are working now because now with being in the situation that we're in, there's been more emphasis put on making sure that that stuff's working. Position relative to a selected course or bearing. Position relative to a glide slope localizer during instrument ILS approaches, and we'll talk about all that as we go along. And it controls the heading select feature. Now, as Larry talked about yesterday, we have an advanced flight control system, which is nothing more than 2 computers that help you fly this aircraft. And Larry said that it provides for several features and ran down a long list of them. And one of those features that he talked about was heading select. Now this aircraft is an IFR cross-country dream aircraft. Because basically what we have is heading select is the ability to tell the AFCS computers how to navigate this aircraft using what's called a heading bug. And all you have to do is roll that heading bug to whatever heading you want it to maintain for you, and this aircraft will go into up to a standard rate turn, roll out on that heading and maintain it until you tell it otherwise. We'll talk more about that as we go along. And then select the navigational equipment to be displayed on each HSI through the HSI mode select panel, which is down there on the very bottom. Controls and indicators. The control itself, the control head itself, is connected to your directional gyro, located in your avionics closet, located between station 95 and 120. 95 being the back of your bulkhead, station 120 being the front of the cabin. On the left-hand side is the avionics closet. And what I like to do to use as reference point is the forward transmission. Why? Because everybody can identify the forward transmission 10 out of 10 times. So if you stand underneath the forward transmission, you take 2 big steps back. Immediately to your left is going to be the flight control closet, the back of the flight control closet. Immediately to its left is going to be that avionics closet, and we're going to reference that a lot. Okay? Because there's a lot of our control heads are in there, our radio control heads, our navigational equipment control heads, 2 vertical gyros, the 2 AFCS computers, and so on, are all in that closet. So you're going to be very, very familiar with that closet by the time we're done. Now, we got one single directional gyro, and it is feeding both those horizontal situation indicators. The compass card itself will turn to display the heading from that directional gyro, and it presents the helicopter heading. It's read by the lubber line. Now, the lubber line is right here, but what you have to keep in mind is, what is this down here? It's a lubber line too. Why does that have to be kept in mind? Because later on, when we talk about that heading select, like anything, it can be tricked. If you think you're going to fly 180 out from the direction you're currently flying, if you roll that heading bug 180 out, it's going to line up with that bottom lubber line. So when you turn on heading select, what do you think the system's going to interpret it as? It's flying the right direction. So therefore, the aircraft's going to do absolutely positively nothing. So you have to keep that in mind. Okay? There's another association with the lubber line that you have to be aware of. If you roll the heading bug greater than 180 degrees out, those computers are smart. Bless you, they're computers. If you roll that heading bug greater than 180 degrees out, those computers are going to say, hey, I can get to your heading faster by going the opposite direction. So when you first turn the heading knob, it's going to create an error signal from that lubber line, and the aircraft's immediately going to go into a turn. But as soon as you roll it out greater than 180 degrees, and it determines, hey, I can go the opposite way and get to the heading you're requesting faster, then that aircraft's going to swing around and start going the other direction to get to it. Now, if it doesn't matter, that's okay. But normally we're in holding patterns, so we have to turn a certain direction, or we have to approach from certain directions. So therefore, we may not have that luxury to allow that to happen. Now, does that mean I can't use it in that situation? Sure, I can use it. What I just have to do is roll it a little slower, not to create or go beyond 180 out. And then once the heading that I want to obtain is less than 180 degrees out, then I just roll the knob to it, and the aircraft will do just fine. But that's the lubber lines that they're talking about. Okay, you should be on page 5 of your handout now. We're going to be at the top, and we're going to talk about the number 1 bearing pointer. There's your number 1 bearing pointer. And the big thing about your number 1 bearing pointer is it is always going to point to the Doppler GPS signal. Now, whether it's a Doppler signal or a GPS signal, it's going to be dependent upon the control head itself, what you have selected. Okay? But it will always be pointing to something. Whether you're using it or not, as long as that Doppler GPS is on, it's going to be pointing somewhere, which we always turn it on. Number 2 bearing pointer, down here at the bottom left-hand corner. The number 2 bearing pointer can either be your VOR signal, or it can be your ADF signal, depending on your desire. So later on, we'll talk about how to dictate which one it is. Course deviation bar. This is your course deviation bar. Along with your course deviation bar, here's your course deviation indicator. And what you have to keep in mind is it's on your compass card. So although you may have that compass card or it may be pointing in one direction, that course deviation bar will still work as advertised. It just may be pointing a different direction, but the increments and the breakdown is always going to be the same. Okay? And that is, when that course deviation bar deviates between the left and the right, it's actually going to tell you how far to the left or to the right of that course line you are. But what you have to keep in mind is, depending on what system we're talking about, those dots have different meanings. For the VOR and the Doppler GPS, each one of those dots represents 5 degrees. For the ILS, it's 1 1/4 degree. Any questions about that? Now, the course deviation bar will work with FM homing, but the course deviation bar, those dots, have no meaning for FM homing. That course deviation bar will tell you if that FM signal is coming from the left or the right of the aircraft, but what you're going to find out is this glide slope indicator is also going to be that frequency strength. So you're going to use the course deviation bar to determine whether you have to steer left or steer right, but then you'll use the strength indicator to determine whether or not you're getting closer or going farther away. Okay, and I can tell you, for the times that it worked for me, it put us in line of sight every time. We never had a problem with it. Okay. Course selector knob, down here at the very bottom. Now what you have to keep in mind with the course deviation bar is it's going to work with your analog system, but it's also going to work with your digital system. So as you turn your course knob, your needle's going to be moving, and so is your digital display up in the top right hand corner, and they will always read the same. You can't have one on one and one on the other. Okay. The range indicator, top left hand corner. The range indicator will always work with the Doppler GPS. Your range indicator in the top left hand corner will always work with your Doppler GPS. It will always be in kilometers and tenths of kilometers. Why do I emphasize that? Because the Doppler GPS can use both military grid reference and lat long. What are the unit of measurement requirements for lat long? Nautical miles and feet. So therefore, this still will not change, even with lat long. It will always be kilometers and tenths of kilometers. It will not change. But the Doppler GPS will. Heading select knob. Your heading select knob is going to work with your heading bug right here. Now, the heading select is only going to be a function with the AFCS on and heading select engaged. That heading select bug and that heading control knob, if you do not have heading select engaged, will do absolutely positively nothing for the aircraft. Okay. Now, you'll notice when we talk about the heading select, it is a process to engage it. And you're going to find out when we talk about it under AFCS in more detail, there's a lot of safety features built into it because of what the system's capable of. Okay? Literally, when you have heading select engaged, it controls the aircraft, or allows the aircraft to be controlled using that knob right there in conjunction with that heading button. And it's a real neat system, okay, especially for cross country. It gives you a little bit of latitude to relax just a little bit, okay. What is the process? First thing, the AFCS has to be engaged. If the AFCS is not on, then heading select will not be available. And then, because both HSIs are completely identical, what's the first thing we have to tell the system?
Which HSI you use?
Which HSI? So down here on the mode select panel, we have a command select button that you will engage. And that command select, all it does is identify which HSI is going to be used to send the signal to the AFCS computer for the heading select process. That command select does nothing else for anything else. Okay? Now what you're going to find out is for us, command select is part of the transferring of control process. So in other words, if I had the controls on the right and we transfer the controls to the left, as well as doing the usual call out response, you got the controls, I got the controls, you got the controls, you will also transfer command select at that time. Now, will the system acknowledge leaving it in one place versus the other? Yep, sure will. It doesn't care who's on the controls. If you do not remember to transfer command select, you may think that you're setting everything up, and when you engage heading select, it's going to listen to whatever the other control head was doing. It's still going to engage. It doesn't know that you made a mistake. So we get in a habit of transferring command select in conjunction with the controls. And it's a pretty well established technique, so we don't really engage or have any problems with that. Any questions about that? Okay. The heading flag. Here's your heading flag. And when we talk about the, oh, wait a minute. Now, we have everything set up. The only thing we have to do now is actually engage heading select, and that's going to be the AFCS control panel. The AFCS control panel is located on that candid cancel on the right-hand side. That's where it's located. Heading select is only engaged when that greenish bluish light, NVG compatible light, says engaged. If it's not lit up, then heading select is not on. And heading select is a feature of AFCS that has to be engaged. It's not one of those automatic features that we'll talk about under AFCS. So it's a process of engagement. It's not just you're going to reach down there and turn it on. If you just reach down there and turn it on, you're not going to know what the aircraft's going to do. It will do something.
How does it display who has command of the system in the aircraft?
When you identify command select down here,
Yeah.
a greenish bluish light will come on and say select, and that's how you know that it's engaged. Now, the other thing about this, and we're supposed to talk about it in just a little bit, is it is a take system. It is not a give system. Okay? So you can't transfer it over to the other side. The other person has to take it from you. Okay? And you're going to find out because of that, there's some safety features built into it. i.e., if you had it selected on the right and you had heading select engaged based on information from the right, and for some reason the person on the left hits that button, heading select will turn itself off. So there's a lot of built-in safety features to make sure that the aircraft doesn't do anything uncommanded. The heading flag. As we look at it, and these flags are going to be identical for the most part. What do I mean by that? If the heading flag comes out, it tells you that you've lost the signal. Lost the signal from where? Where? Not the VOR. We're talking about the compass card. So where's the signal going to be coming from that's lost? the directional gyro. Okay, the other time that that flag's going to come out is if we lose power to the system. Whether we lose it to the control head itself or lose it to the indicator itself is irrelevant. The flag will come out. That should take you to the top of page 7. The to and from arrows, and we don't have a very good picture of the to and from arrows, but they would be right here. And like any to and from arrows, they're going to be telling you whether or not am I heading towards my signal, whatever I have selected, whatever navigational system I have selected, or am I heading away from it. Now this arrow, it just slides back and forth. And that's why you can't see it in here. But keep in mind, because that's embedded into the compass card, those to and from arrows will rotate around accordingly too. Nav flag. The nav flag is a tricky flag in the fact that, one, it's embedded into the compass card. Here's where it is. 2, the nav flag is going to be associated with the different navigational aids that we have on the aircraft. But we don't always use all the navigational aids of the aircraft. So if you're not specifically using the one that failed, you won't get the nav flag. So what are we talking about? The nav flag is going to work with the VOR, the Doppler GPS, the FM homing signal. So if I'm not using the FM homing signal and the FM homing fails, that nav flag won't come out. But now if I'm using the signal and it fails, then that flag will come out. Whether I lose the signal or whether I lose power is irrelevant. It's going to come out for both reasons. Any questions about that? The fixed helicopter signal, symbol. Do we need to talk about that? Okay, that's common to all HSIs. Glide slope pointer. Now we do have to talk about the glide slope pointer because this is a little different, and every HSI is a little bit different on how they handle this. Okay, so what we're going to do is we're on the bottom of page 7 of your handout. In order to make sure there's no confusion, I like to read it directly out of here so we don't make any mistakes. Because what people try to do is they try to, instead of a pointer and the square, they try to associate it one with the glide slope and one with the helicopter itself. And sometimes they get it discombobulated and they get it backwards. So we're just going to make sure. When the pointer is above the center, so here's the center. So if the pointer is above it, then the aircraft is below the glide slope. So the center is the aircraft, the needle is the glide slope. Okay? Is why people try to associate it that way, which is no harm, no foul, but we got to make sure that we're on the right shit of music right off the get-go, because it's very easy to get which one's the helicopter and which one's the glide slope confusing, and that's why I like to do it this way. So when the pointer is below the center, then the aircraft is above the glide slope. Again, the center being the helicopter, the pointer being the glide slope itself. Any questions about that? Now, the other thing that it will work with is FM homing. And basically, the stronger the signal strength, meaning you have to be pretty close to it, the higher up that needle will go. And like I said before, the times that we've used it, it works awesome. It's always got us in line of sight. Okay, and as long as they can transmit on FM, we can locate them. And it works very well. Whether it's a vehicle, whether it's a downed aircraft, whether it's just a patrol. As long as they have FM capability, that system works just fine in locating them. HSI mode select, down here at the bottom. This is your HSI mode select panel. This is what it looks like. This is what it looks like out on the aircraft. Okay, we'll pass this around and let you look at it. Switches are push on, push off type. Now, as we talk about them, The ones for the VOR, the Doppler GPS, and you'll notice this one just says Doppler. It is now Doppler GPS, and you will see that it's out on the aircraft. It's already been modified for that. The initial 128 Alpha system was a Doppler-only system. In the CH-47D, we're now flying with the 128 Bravo, which is a combination Doppler GPS, and the labeling now indicates that accordingly. Although in here it only says Doppler. And FM homing. These three right here work in conjunction with your course deviation bar. That's what they work with. Now, as we talk about them, everybody likes to know, well, if I have VOR on the right, can I have another one on the left? Either Doppler GPS or FM homing. And the answer is yes. I can have VOR selected on the right, I can have VOR selected on the left. As long as I keep one thing in mind. And that is, if I have VOR on the right, whatever frequency is used on the right is the same frequency that's going to be used on the left. Okay? The right can't tune up one frequency and the left turn up another frequency. Anybody want to take a wild guess why? One control head, one receiver, that's it. That is the limiting factor. Other than that, they are separate indications. Any questions about that? And that's going to be applicable to all of our indications. VOR, Doppler GPS, ADF, when we talk about ADF here in just a little bit, that's going to be appropriate for all of them. Why? Because we're limited in the fact that we only have one control head. So I can only tune and identify one frequency at a time. Okay. Command select. As we talked about command select, that's going to be used with the heading select feature of the AFCS, the Advanced Flight Control System. That's what it's going to be used for. And all it's doing is identifying to the computers which HSI signal do you want those computers to process. Any questions about that? All right. Now the bearing. The bearing is to the far right, and this is where you determine what your number 2 needle is going to be pointing to. That's all this does. Okay, these three controlled my course deviation bar. Command select was for heading select feature, and the bearing is going to be used to determine what my number 2 needle is going to be pointing to. Is it going to be processing the VOR signal? Is it going to process the ADF signal? Keeping in mind that on one side I can have VOR, on the other side I can have ADF. Again, just like we just talked about, I can have VOR on the right, VOR on the left. That's okay too, as long as they're processing the same signals. You can't have one frequency for the right, one frequency for the left. Why? Because the limiting factor is the fact that we only have one control head. Any questions so far? Okay. The next thing we're going to talk about down here on the bottom are your marker beacons. As we look at your marker beacons, you have your outer marker, middle marker, inner marker. Some only have outer markers and inner markers, but we have all three. And as you can imagine, not only is it going to light up as we pass through the different marker beacons, you're also going to get an audio in your ear denoting whether or not and what marker beacon you're passing through, keeping in mind that it starts off low, and as you get closer to the inner marker, then it gets louder and louder. And you can see on your handout, the outer marker is 400 hertz. The middle marker is 1300 hertz. And of course, the inner marker is 3000 hertz. So in other words, as we're progressing, it's just getting louder and louder. Why blue-green? Why is it writing up blue-green down here?
NVGs.
NVG compatible. And everything we have on the aircraft is NVG compatible. So everything's going to be blue-green. Okay? One thing that I did fail to mention with the VOR, or excuse me, with the bearing, is it's a little funny in the fact that the only time you may see it not lit at all is when you initially power up the aircraft. Okay? But once you engage either VOR or ADF, something's always going to be shown. Whether you're using it or not, it's always going to be shown. Why? Because it's a push-on, push-out type of system. When I push it on, it's VOR. When I hit it again, the button's going to pop out, and then it's going to go to ADF. And so there's not an off position per se. So it's like anything else where when you first power up the aircraft, because it's not been told one way or another, it may be off at that point. But once you designate, it's always going to be lit for something. There's not a off position. Any questions about that? Okay. I just wanted to point that out. Now, for testing the outer marker beacons, there are 2 test procedures available. Now, the flight line will tell you exactly which one they want, okay, because we've danced around. At one point, we were doing both tests. Then they went to just one test. And depending on, I don't know where we're at right now as far as which one they want. But the 2 tests are as follows. You can push any one of the marker beacon buttons, and what will happen is as you push it and hold it, all 3 lights will light up. And they will stay on until you let go of it. The other test is going to consist of identifying the VOR control head, and down at the very bottom left-hand corner is a marker beacon test switch. And it will do the same thing. So the IPs will tell you exactly which test they want you to do. I think that just recently changed on which one we were doing. Any questions? Okay, then we'll go ahead and get started back up. Now we're going to talk about our rate altimeters. Now this one's a little bit tricky in the fact that when we talk about the rate altimeters themselves, the front of it and the controls are all identical between the left and the right. And if the aircraft's been modified, we have one by the center cargo hook now for the flight engineers, which is why you'll see an F by that one. Okay? But what you're going to find out, reality is, the only rate altimeter system that we actually have on the aircraft is the pilot's side. The co-pilot slaves off the pilots. If the one is installed by the center cargo hook, it slaves off the pilots. So the pilots is the only true rate altimeter. Now why is that a little bit tricky? Because when we talk about water landings, Larry told you yesterday that both AFCS systems have to be functioning, and both the pilot and co-pilot's rate altimeters have to be operational. And so there's always a little bit of confusion. Well, if I only have one system, why can't I just say that the rate altimeter is operational? Because both displays have to be identical and they both have to be working to do a water landing at night. And if you've never flown over water at night, you will not have a concept of what a difference that rate altimeter system makes if you're trying to do a landing to the water. Okay, because at night you have no depth perception. And it's very, very easy to get going too fast, and that water will crack that hole something fierce. Okay, so they do require both rate altimeters to be working. But when we talk about the system, we only technically have one rate altimeter, and that is on the pilot's side. Is everybody tracking that? Everybody understands that? Okay. This rate altimeter itself is good to 1,500 feet. Why? Because when we talk about the process of how it works, you're going to understand that based on that signal, as we get higher and higher, that signal is going to deteriorate, which makes it unreliable beyond 1,500 feet. Now, it will get a little bit confusing because we're going to base everything off of 1,500 feet, but you're going to find out as you get to know these rate altimeters, as you use them, most of them will go above 1,500 feet. But the accuracy is only guaranteed up to 1,500 feet. And that's why we tell you that they're only good to 1,500 feet. Plus the analog will definitely stop. Now, the pilot's rate altimeter is connected to the #1 AFCS system, the Advanced Flight Control System. Why is that going to become important to know? When we talk about rate altimeter hold. Okay, that is a process of the #1 AFCS computer, but it is receiving a signal from the pilot's rate altimeter only. So if the pilot's rate altimeter goes belly up and you had altitude hold engaged, what are the possibilities? It's going to fail too, thrust runaway, and we'll talk more about that under AFCS, but there's a lot of potentials if you have altitude hold engaged and whatever signal is being processed, whether it's barometric pressure or whether it's the rate altimeter, there's a lot of possibilities of what that system can do to the aircraft itself, and we'll talk more about that under AFCS. Okay. Indicating system. We have two indicating systems. They will be identical, or should be identical. You have the analog system, which is your needle, and you have a digital display that's going to correspond with the analog, plus or minus what? Anybody doing pre-study? Plus or minus 5 feet. Plus or minus 5 feet. Difference between the analog and the digital display. The low knob, located on the left side of the control. The low knob is going to serve two purposes, and that is it's going to turn the system on, as well as it's going to control this low bug. Now when you turn the system on, what's going to happen is that low bug is going to be hidden. As you turn it on, that low bug is going to come out, and then all the lights are going to start lighting up. And you're going to take that low bug and you're going to preset it at 100 feet. Now the first thing that everybody asks, why 100 feet? Because when we go to do our test for the rate altimeter, which we're not going to do it right away, there's a special spot in the checklist that will tell you to do the actual test, but we're going to go ahead and set up everything for that test. And that's why we're going to take it to 100 feet. Any questions about that? Okay. The high knob, located on the right-hand side. Now, there's two primary functions of it, but there is a third function incorporated into it if an aircraft is modded for it. And we'll talk about that as we go along. The first thing is, of course, it's going to control the high bug. The high bug, we're going to go ahead and preset it at 800 feet. Why 800 feet? In anticipation of doing the test. That's why we're taking it to 800 feet. The other thing incorporated into it, this is where you push to test the system. And we'll talk about the test procedure here in just a second. But this is the button to push. The third thing that it does, that if it's incorporated, if the aircraft is modded for it, it now has an audio attached to the low and high knobs. Or the low and high needles is actually the bugs. Okay? And if you go below that low bug, in conjunction with the light, you will get altitude low, altitude low. And if we're doing a sling load, that can get very, very annoying. So what you also have incorporated into the high bug, or the right knob, the high knob, is a method of reducing the volume. Now I'm trying to be very careful on how I say this. It reduces the volume because here's what's going to happen. It's going to be, when you first crank it up, it's going to be at the highest audible possible. When you push it, it's going to cut that in half. When you push it again, it's going to take that half and cut it in half again. When you push it a third time, it's going to cut out the audio altogether. You push it one more time, it goes back to high.
Is it on both co-pilot and pilot, or is it just the pilot?
Just the pilot's one will do it. Okay? Why? Because again, that's the only true rate altimeter. The left and the one that's in the hole only mimics what's going on with the pilot side. Matter of fact, if you turn the co-pilot's on, you turn the one in the hole on, if the pilot's one is not turned on, then those other two won't light up right away. Any questions about that? And same thing with off. You can turn them off, but until the pilot turns their off, the lights won't go out. Okay. Caution lights. You got a low light and you got a high light, and they will light up NVG compatible blue-green, and basically they are going to work in conjunction with the high setting and the low setting, wherever you set it. Now, initially, they were turning down that volume and turning it off. If you don't know, we had several incident accidents right off the get-go. Flying too low, too fast. So now, they're making people leave them on and actually using the high and low bugs. Specifically the low bugs. That way, we're not hitting anything like we used to because of optical illusion. If you've never flown in a desert environment, the mirages and the heat coming off the sand produces an optical illusion that sometimes you may be lower than what you think you are. And that's why we had a lot of them, and that's why unit SOPs are pretty much saying, don't turn it off, use it.
Do they have like a reset feature anywhere, like on the somewhere on the controls, or just you have
No,
to get
sir.
above that altitude to make it go up?
You got to get above that altitude to make it go out, which is why everybody's turning them off. Okay? That's the only way. Now, I can't vouch for what you have and don't have.
I know what they have. I'm just curious if they incorporated this.
No, they did not. Okay. Anything else? Okay, the off flag. Here's your off flag. And when we talk about the off flag, of course, when I turn the system off, the off flag's going to come up. That's kind of a no-brainer. But it has another association, another thing you have to be aware of. And that's as you climb up through 1,500 feet, the system will give you the appearance that it has turned itself off. And it has turned itself off. But since you did not turn off the knob, the system is actually still on. So although you went above 1,500 feet and the off flag came up, as soon as you descend below 1,500 feet again, then it will reestablish itself and everything will come back on. And the off flag will, of course, go away. But that's the off flag. And we'll talk more about the operational characteristics in just a second.
I got a quick question. This may sound silly, but this aircraft, when it hovers ass end low, why are the red altimeters up by this picture up in the front?
That's where they put them, but you're going to find out. You have to keep that in mind. And you'll know right off the get-go, is it reading the height of the nose on that aircraft, or is it set for the landing gear? And we'll talk about that here in just a second. But you're 100% correct. Okay, each one of the rate altimeters has its own dimming control knob so that you can change the intensity per your side. But keep in mind that they will go bright enough that if you don't keep them at a reasonable rate on both sides, they will shut down the goggles. That's how bright they can go. Okay? If only one turns down theirs, the other one will remain bright enough that it will still block out the goggles. So you have to keep that in mind. Now, that also becomes important to know because of a second feature that you have to keep in mind. And that is, if the person before you or the aircraft was used for MVGs the night before, when they turned down the aircraft or they turned off the aircraft, where do you think they left that control knob? They left it set for them for night vision goggles. Well, you can crank up the aircraft the next day on a bright sunny day and it'll appear that it doesn't work. So you have to keep that in mind. Don't forget to check those. Any questions about that? Okay, limitations. The radar altimeter system is limited to 1,500 feet. Keep in mind, gentlemen, that we know that in a lot of cases the radar altimeters will go above 1,500 feet. We know that. But the reliability is only guaranteed up to 1,500 feet. So what do we mean by it doesn't necessarily go out? What will happen is even though you're above 1,500 feet and the needle has buried itself or it's hidden itself, your digital display may still be on and the off flag will still be down. And I've seen them go as high as 1745. But it does not change the reliability of the system. It's only good up to 1,500 feet. Reality is, wherever it turned itself off finally, as you descend, that's where the lights will come back on. Just something to keep in mind, okay? Now, when you go above 1,500 feet, what's supposed to happen is the needle's going to bury itself. All the lights are going to go out to include the high and low bugs, and the off flag is going to appear. That tells you you're above 1,500 feet. Once you descend back below 1,500 feet, then the digital display will come back on and the analog needle will start to move in conjunction with your altitude. Any questions about that? Now, the system itself is only good to 45 degrees of bank and angle as well as pitch angle. Why? Because as it's already been brought up, the antennas on this aircraft are underneath the pilot and co-pilot's seats. The pilot signal, or the pilot's antenna sends the signal, the co-pilot's antenna receives the signal, and both signals are processed by the, which one? Pilot's radar altimeter. And then the pilot's radar altimeter will display the indication, the co-pilots and the one in the hole will slave off of what the pilot is indicating. But now, if I put this aircraft in a 45-degree bank, where are those antennas going to be pointing off? Off into la-la land. If I have a 45 degrees nose low or high, again, what's going to happen to those antennas? They're going to point off in la-la land. Any questions about that?
Yes, sir. When it does that, will it just give it an accurate reading, or will the flag come up?
It depends on what it's reading. The same thing will be applicable. If you go above 1,500 feet and it reads above 1,500 feet, then it's going to fool itself and it's actually going to go ahead and do everything that it's supposed to say. The needle will go above 1,500 feet, the digital display will go out, the off flag will pop up. If it's less than 1,500 feet, then it will continue to read. We just know that if I'm at 100 feet off the ground, but I have a 45-degree bank angle and those antennas are pointing off in la-la land, the radar altimeter itself may read 900 feet based on the signals. And keep in mind, if it shoots off in la-la land and it never receives a signal back, then the same thing's going to be applicable. Anything else? Alrighty. And that covers the bottom of page 12. Normal operating procedures. Normal operating procedures. You have to pay attention to the checklist because it'll tell you radar altimeter set as required. This is part of that process, but the only thing you're going to do at that point is power the system up. You're going to go ahead and turn the power on, and you're going to take your low bug to where? 100 feet. You'll take your high bug to 800 feet, and then you'll leave it alone. Later on in your checklist, it will tell you to actually go through the process of doing the test. And we'll talk about the test procedure here right now. Any questions about that? All right. So when I test it, what's going to happen is you're going to push the test button and hold it. If you push it and let go of it, the test is going to stop. You have to push it and hold it. And what you're going to see is the needle, of course, will be down here. The low light will be on. Why will the low light be on? Because your needle is below your low indicating bug at 100 feet. When you push the button, what's going to happen is your analog needle is going to come up. In conjunction with that needle movement, you're going to get a digital display. And I'm kind of slowing it down. You're going to find out that it's pretty quick on the aircraft. So you'll be on top of it. You push the button, hold the button, the analog needle comes up with the corresponding digital display. As it goes through the low bug, the low light's going to go out. As it goes up through what? 800 feet, the high light's going to come on, and then it will go to, oops. Okay. See, I get overly excited too. Okay. Now, here's the thing, gentlemen. Depending on where you read, we're going to accept two answers for where that analog needle is going to end up. Okay? In chapter 3, it says one thing. In chapter 8, it says something different. What are the two answers? Where that analog needle is going to end up? It's going to be at 1,000 feet, plus or minus 100. Or it's going to be 900 to 1,100 feet, depending on where you read. Now, 1,000 plus or minus 100, 900 to 1,100, go figure. Now, how many people have had prior experiences with red altimeters? Okay, now watch this. Where does it normally end up, sir?
It depends. I mean, you have different parameters for when it's actually set. Some guys are allowed to read plus or minus 3 feet.
Okay, that's not what I'm looking for. When you do the test, where does this needle usually go to?
About 1,100.
It normally goes to 1,000. Guess what people try to put on the test?
No.
1,000. Okay? Why? Because they've had enough experience with it to know that on an average, normally, most aircrafts take it to 1,000 feet. But 1,000 feet is not what the Dash 10 says. We tracking? It says either 1,000 plus or minus 100, or it says 900 to 1,100 feet. Those are the only two acceptable answers. If you put 1,000 feet, you're going to get your feelings hurt. And I don't like seeing people's feelings get hurt. Any questions about that? Okay, now, what's going to happen is I'm going to let go of it, and as I let go of it, as it comes back through or below the high bug, excuse me, the high light's going to go out. As it comes back below the low bug, the low light's going to come back on, and then it's going to go back. Now, and here's what he was trying to tell us, where's it going to end up? It's going to end up between 0 and 3 feet. Based on what? If you look at where our antennas are located, you'll notice that they're underneath the nose of the aircraft, which is in an up angle. Now, some of the units set them to where the landing gear is, so they will be reading 0. We tried to standardize it in the past. Some units comply, some don't. So therefore, you may still see it reading between 0 and 3 feet, or it's going to be reading 0 itself. Any questions about that? Any questions about the test procedures? In-flight operation. We all know how to read it. Again, you're going to get a digital display that's going to correspond with the analog needle. From 0 to 200 feet, you'll see how the increments go. But then once you go above 200 feet, it changes to 500 feet, then 1,000, and then 1,500 feet. And the increments keep changing. Now, the other thing we need to keep in mind is this has what type of function? Why are we talking about it? It has a unique feature to the CH-47 called rate altimeter hold. It will actually maintain the altitude of the aircraft via this signal. Which signal? What's pilot's rate altimeter? Through which computer? The number 1 AFCS. Are we all tracking on that? Now, reality is we don't use it a lot. Okay, I can tell you I've only used rate altimeter hold 5 times in my entire career. And all 5 times have been over water. That's about the only time I've ever seen it used. Okay, now everybody says, well, what about sling loads? Sling loads are not hover practice. I promise you, you want to see some frustrated crew members? Use sling loads training as hover practice. Okay, the goal of sling loads is to get in, get hooked, get checked, get in the air. It's not hover practice. So we don't use it for that. Any questions about that? All right. Any questions about your rate altimeters? We're going to talk about your attitude indicator now. Now, an attitude indicator is an attitude indicator is an attitude indicator. Okay? So why do we have to talk about a difference? First off, in the CH-47, we have 2 attitude indicators, also known as VGI, vertical gyro indicators. You have one on the pilot side, you have one on the co-pilot side. Go figure, right? Now here's where your knowledge is going to be important. Those indicators are completely separate indicating systems. The pilot's vertical gyro indicator is completely separate from the co-pilot's indicating system. Which means what? Which means we not only have 2 attitude indicators, we also have to have 2 what? Vertical gyros. Those vertical gyros are going to be located in the avionics closet between station 95 and 120 on the left-hand side of the aircraft. The other thing you have to keep in mind, here's where it gets a little confusing. If you're paying attention to the text, the number 1 vertical gyro is going to be feeding the co-pilot's attitude indicator or the co-pilot's vertical gyro indicator. The number 2 vertical gyro is going to be feeding the pilot's attitude indicator or vertical gyro indicator. Why is that important? What does everybody try to do? Associate pilot with number 1, okay, which is a natural tendency. But the aircraft systems doesn't care about your title. Left side of the aircraft is the left side of the aircraft. Right side of the aircraft is the right side of the aircraft. And that's what it abides by, not what your title is up front. Any questions about that? All right. Trim knobs. You got the upper knob and the lower knob. The upper knob is going to be for your roll. And just like normal, 8 degrees left, 8 degrees right. That's normal for most attitude indicators. Any questions about that? The lower knob is going to be pitch attitude, keeping in mind that when we talk about pitch attitude, it's going to be 20 degrees nose up, 20 degrees nose down. That's pretty much standard. Any questions about that? Now, you'll notice on page 15, you have an operator's manual note. This is directly out of the Dash 10. And that note says, Rapid rotation of the pitch and roll trim knobs on an attitude indicator may cause abrupt pitch and roll attitude changes with the AFCS on. Now, why does that become a problem? Because later on we're going to talk about the fact that the advanced flight control computers are not processing the vertical gyro indicating signals. And what did we just say about the system? They're completely separate, right? The number one vertical gyro, as well as feeding the co-pilot's attitude indicator, is going to feed the number one AFCS computer. The right vertical gyro, as well as feeding the pilot's attitude indicator or vertical gyro indicator, is going to be feeding the number two AFCS computer. And there's a lot of confusion as to why that caution or why that note is there. And that's because if you look in our avionics closet, what you're going to see is your number one vertical gyro, your number two vertical gyro, your number one AFCS, your number two AFCS. Now the mindset, based on what we teach, is that this signal goes here as well as goes to the co-pilot's VGI. Agreed? So this signal goes here as well as going to the pilot's VGI. And that's what people picture. But now, in picturing this, the association between those knobs gets lost. Because what people picture is two separate paths. But the paths are not separate. What happens is, this is a relay. This signal goes to the relay and then splits. So when you rapidly turn those knobs, what will happen is it will cause power surges to jump back and forth, and then that's what's going to cause the erratic behavior in the advanced flight control computers. Okay, now, why else does that become important? Because in a little bit, we're going to talk about an indicator failure versus a gyro failure, and what you can and cannot do about the two different problems. That's the other place that this is going to factor in. Okay? Now, the electrical power requirements. We're not going to make a big deal about this right now because of the fact that if I tell you something works off the number one AC bus, what does that mean to you? Zip, zilch, not and nothing. Why? Because you haven't had an electrical class yet. But like anything else on this aircraft, if we're talking the number one system, then it's going to be powered up via what? The number one electrical system. If we're talking number two system, it's going to be powered up off the number two system. And that's easy to say, but there's a lot more complications into it when we talk about a generator failure with a bus tie or without a bus tie, and we'll get into that under electrical. Okay? And a lot of people start to confuse that with just being able to identify where the power source is. Right now, all you need to know is the number one system feeds off the number one electrical system, AC. The number two system feeds off the number two AC electrical system. Any questions about that so far?
We're not AFCS light switches in both. There's no information shared there at all. Those are two entirely independent.
Okay.
When referred to the attitude indicator.
Okay, now say that again.
When you have the AFCS light switch in both,
Yes, sir.
is there no information shared between those two?
No, sir.
Okay.
No, sir. Everybody hear the question? When you select AFCS both, One thing you have to keep in mind, and we'll get into it under both AFCS, and we'll get into it under flight control hydraulics.
Yeah, I didn't mean to jump ahead.
No, that's okay. That's okay. Okay? That's why we're doing it this way, because these are concerns and these are questions. Okay? But what you're going to find out is both those systems are completely independent of each other. Okay? What you're going to find out is when we talk about that switch, selecting both, the only thing you're actually determining is whether both systems have hydraulic pressure or not. Okay? The mindset is when I turn a system off, the mindset is, what am I turning off?
Systems hydraulics.
No, that's not the mindset. That is the fact. Okay, but what is the mindset? When I say AFCS system select switch off,
Turning the computers off.
turning the computers off. What you're going to find out, gentlemen, is you are not turning off the computers. All you're doing is depriving the system of the necessity of the hydraulic fluid or the required hydraulic fluid. That's all you're doing. Those computers are going to constantly be processing for you. All you're doing is, by selecting off or on, is determining can those systems actually move for you or can't they, by whether or not you have hydraulics there or not. And we'll show you where they actually is turned off later. Okay? Anything else? Good question. Now, both indicators should erect within 30 to 90 seconds. Based on what? Based on how fast those gyros spool up. The faster they spool up, the faster those needles will erect. The slower they spool up, then it might take a little while for them to finally stabilize and be erect. And again, it has 30 to 90 seconds. I've never seen them take that long. Either they're going to spool up and they're going to do just fine, and they usually do it pretty quickly, or they're not going to spool up at all. Any questions about that? Okay, now, on the pilot and co-pilot's instrument panel, you have what's called a VGI switch. Now, there's a misconception about that switch. Okay? What that switch does is it takes that indicator and slaves it to the opposite gyro. I'll say that again. It takes that indicator and slaves it to the opposite gyro. What is the misconception associated with that switch? That it takes the indicator and slaves it to the opposite indicator. And that is a misconception. Where does the misconception come from? The switch says VGI switch. And so therefore, when people associate this switch, they think that it's slaving one indicator over to the other indicator. It is not. It is not. Now, why does that become important to understand? Because of the fact that we have two potential problems that can affect this aircraft. We can have an attitude indicator failure, or we can have a gyro failure. Everybody concur? I can have either problem. Now, that brings, what is this switch associated with? Is it associated with an indicator failure? Or is it associated with a gyro failure? It's going to be a gyro failure. If the indicator goes belly up, then the indicator's belly up. There's nothing you can do about it. We tracking? Okay. So now, what becomes the mindset? What becomes the process that I have to be able to figure out? Is it an indicator failure or is it a gyro failure? So now I need to be able to understand, how do I determine that? How will I as a pilot know whether or not the gyro has failed?
Put it into emergency.
What?
Put the VGI from norm to to emergency and see if it's your.
And that's the number one answer. But what if I could tell you there's a way that you'll know whether or not you have to move that switch at all right off the get-go? Would you like to know that? You think that's important? And especially since it's associated with how does the system work? We said that the attitude indicator, the vertical gyro indicator, is receiving a signal from the vertical gyro. But we also said that same vertical gyro is sending a signal to where? AFCS. Now, that's why the misconception about this relay comes into place. Because I know that the computer is not processing this signal. So when people picture it, they picture this. They don't picture this. Are we tracking so far? So how will I know if I have a gyro failure versus an indicator failure? I will also lose the associated AFCS with a gyro failure. If the indicator failure or the indicator fails, the only thing that's going to fail is the indicator. Any questions about that? Clear as mud now, right? Makes a lot of sense. Okay, so now, how will this process occur? How will I start to know that I'm having problems? First thing you're going to notice is as you're flying along, your indicator might get a little bit squirrely or erratic or whatever you want to call it, but it'll do something. And then eventually when it completely fails, you're going to get a funny look and you're going to get an off flag. So far, what do I know? Just by what we just talked about right now, just right now, what do I know I have?
It's not an indicator failure, you just got that off flag.
Something's failing.
Something's failing. It could be the indicator, it could be the gyro. We're not sure yet. So what else do I need besides this? Now I need to look at my master caution panel. In looking at my master caution panel, if my AFCS, the associated AFCS is on, off light's on, then I know I have a gyro failure. If the associated AFCS off caution capsule is not on, then I have an indicator failure. Okay, here we go. You ready? Which one can I fix?
Gyro.
The gyro failure. How do I fix it?
The other gyro.
Okay, now let's make sure we're all on the same sheet of music. It's easy to say, slave it to the other gyro, but how do I do that? If this is the indicator that went belly up, and this is my co-pilot's indicator, and I determine it's a gyro failure, then I'm going to take this switch from normal to emergency. And this indicator will erect itself back up. But what will not fix itself? The AFCS. And let's go ahead and nip it in the bud. Everybody says, well, why did they do that, Tom? And the answer is, these vertical gyros cannot handle providing signals to both AFCSs. It puts too much drag on the gyros. And that's why the best they could do was give you the indicator back. Any questions about that? Okay. Now, we talked about that normal and emergency switch. The next thing we need to talk about is what is the procedure. You're going to find out in the in the checklist, according to the checklist, at one point it's going to tell you to take that switch and put it in the normal position. At startup, it's going to tell you to put it in the normal position. I'll say that again. At startup, in accordance with the checklist, it will tell you to take that switch and put it in the normal position. In the normal position, the number 1 vertical gyro is connected to the co-pilot's indicator. Number 2 vertical gyro is connected to the co-pilot's vertical gyro indicator. Now, later on, in the checklist. It's going to say VGI switch as required. At that point, if I have a write-up in my book that says the number 1 vertical gyro is in op, at that point, then I'm going to do what? I'm going to take the pilot's emergency switch, and I'm going to take it to emergency at that point. In which case, that indicator will now erect itself. Okay, so what's the question? Why didn't I start that way to begin with? If I already knew that there was a write-up in the book saying that I have a vertical gyro problem, why didn't I take that switch to emergency right off the get-go? And the answer is, in spooling up, they didn't want both indicators connected to a single gyro. It slows it down, it drags it down, and it could cause premature failure, or it could reduce the life expectancy of that gyro. So basically what they want to do is allow both those vertical gyros to spool up their indicators and their indicators only, but later on, if we need to, we can go ahead and hook it to the emergency position, which takes the bad vertical gyro out of the picture. And now both indicators will be connected to one gyro. But what else do I have to still keep in mind?
That AFCS is in op.
That AFCS is going to remain in op. So we are either going to fly single AFCS, or we're going to fly both AFCSs off. Keeping in mind that the AFCS is a luxury item. It is not a required system, except for 3 things, and we'll talk about that under AFCS class. Any questions? What?
Landing in water at night.
Landing in water at night is one of them. What else? You all want to knock them out?
Airspeeds.
Airspeed restriction, but that's not what I'm looking for. You can't hook up a sling load. You can fly a sling load, but you can't hook up a sling load with an inoperative AFCS. And you cannot go IMC. Those are the 3 requirements for you have to have AFCS. And you have to have both AFCSs operational. Any questions about that? All right. Now, the next system we're going to talk about is a very, very unique system, and it's going to be brand new to all of you. And that is your cruise guide indicating system. Now, we have to correct and make sure that you understand. The cruise guide indicating system was intended to get the max performance out of the aircraft. What do we mean max performance out of the aircraft? Max airspeed, max bank angle, and max load carrying capability. That's what it was intended for. Okay? It's no longer applying that way anymore. As a matter of fact, go to your practical exercise, go to question number 3, and cross it off. Go to your practical exercise, go to question 3, and cross it off, because it no longer applies. Now, just so everybody understands where that came from. What used to happen is after I did my performance planning, as I was flying along, if I got to whatever my V&E was on my performance planning card, if I was still well within my green band, I could bump up my airspeed. If I was in a bank angle and I was still well within my green band, I could increase my bank angle. And of course, whatever load we took off with, we were already at. But we would have known if we were putting any stress related to the load that we were carrying. Okay? That's what it was intended for. So now, how is it intended? Now it's intended in a little bit the opposite way. If, after doing my performance planning card, if I find out that my max cruise speed or my max V&E for the day is 154 knots. If I get into the yellow band before I get to 154 knots, I'm now limited to the green band. Now what you're going to find out is we already know whether or not we're going to do that when we do our performance planning. It's already factored in. So that should not be a factor. That should not be a problem. Other than that, I can't explain any other usage for the cruise guide indicator except for if, based on the flight envelope that you are in, it is measuring stress. That's what it's measuring. Okay? Where's it measuring stress? It's measuring stress for both the forward and aft rotor systems, the forward and aft vertical shafts. Okay? Now, the first thing we have to understand is that this system is going to work as long as the longitudinal cyclic trim actuators are functioning. So the first thing we need to talk about is what is a longitudinal cyclic trim actuator? They are two electric motors connected to your swash plates. Okay? They're connected to your swash plates, and we'll talk more about that here in just a second. We'll actually show them to you. That is what those strain gauges and the fixed links, that's what they're measuring stress based off of, caused by that system either working or not working. And what do we mean by that? Here's what's going to happen. On the pilot's side, and this is a unique instrument to just the pilot side. There isn't one on the co-pilot side. What you have is a green band. As long as we're in that green band, we're not putting any unusual stress on critical components, the rotor system, and the shafts. Yellow band, we know, is a avoidance area. We can go into it, but we don't want to stay there very long. And then you have the yellow and red, where we don't want to go into that at all. Now what you're going to notice is my indicator on this picture is not modified. The ones out on the aircraft, this yellow and red band has actually come farther into here. Why? Because what they're finding out in Afghanistan is at the pressure altitudes that they're operating at, they were putting a lot of stress on the forward transmissions and the vertical shafts. And therefore, that's why the change came out. We'll talk more about that under performance planning. Okay? Now, you have a white band inside the indicator, and that is part of the test process. You have a switch right here. If you select the forward indicating system, you're looking for the needle to go into the white band. As long as it goes into the white band, you're okay. You let go of it, it's going to come out immediately. You go back to the aft, you're looking for the needle to come back into the white band. Now, it's going to tell you in an operator's manual caution, do not do the test while the rotors are turning. Not because you'll do damage to the aircraft, not because you'll hurt the components, but because you'll get an erroneous entry. That's the only reason why. A lot of people think you're going to damage something. You're not going to hurt anything. All you're doing is checking the electronics. That's all you're doing. It's not moving anything. It's not causing anything to be moved, and therefore you're not going to hurt anything. You're just going to get a sporadic reading if you did it. Any questions about that? Okay. The cruise guide indicator itself. We talked about the indicator. Needle excursions into the yellow band we avoid. We already talked about that. Now we're going to talk about the strain gauges itself. Here's the strain gauge. The strain gauge is connected to the fixed link. All it is, here's your fixed link. And all you have is a series of diodes and pickups. And what is happening is basically we are creating a magnetic field around right here. If we put tension or torque or strain on this shaft, what's going to happen to that magnetic field? It's going to change, and that change is going to be interpreted as stress. Okay? Now, we said in order for that system to function properly, what other system had to function properly? The LCTs. This is your longitudinal cyclic trim actuator. The longitudinal cyclic trim actuator is going to control cyclic tilt, cyclic feathering in this aircraft. Okay? As pilots in the CH-47 aircraft, you do not create cyclic tilt, cyclic feathering. You create what's referred to as differential collective pitch. Meaning what? Meaning when you put in forward cyclic, you're causing all the forward rotor blades to collectively and evenly decrease. You're causing the aft rotor blades to collectively and evenly increase, pushing down on the nose, pulling up on the tail. And this aircraft takes off just like any other aircraft. But then what's going to happen is as you increase your airspeed, these longitudinal cyclic trim actuators are going to start programming to extend or retract, putting in that tilt into the rotor discs. Now, here we go. The symmetry of lift is going to be compensated for one of two ways. Either cyclic tilt, cyclic feathering, or blade flapping. So when we talk about the longitudinal cyclic trim actuators, because they are providing cyclic tilt, cyclic feathering, they are now compensating for that blade flapping. By reducing blade flapping, they're going to reduce stress on the airframe and the key components. The other thing that's going to happen is by those longitudinal cyclic trim actuators programming, it's going to level off your fuselage. And that's how it's reducing stress. The stress that this is going to indicate. We'll talk more about the LCTs under both AFCS and under flight controls. Any questions so far? Now, it seems like I left you hanging about the cruise guide indicating system. The other thing we need to make sure is we understand is why do we need the longitudinal cyclic trim actuators? Okay? And because in this aircraft, as pilots, you create differential collective pitch, we still have to produce cyclic tilt, cyclic feathering, agreed? And that's what the LCTs are doing. Now, just so everybody understands, here we go. Why do we need them? This is the rotor. I'm the aft vertical shaft. Just so everybody understands, if we didn't have the LCTs, what would happen is you would have a look like this. And just imagine an 8-foot shaft. Okay? I'm only 5'8". Okay? But if we did not have the LCTs, what you would have is based on aerodynamic tendencies is it would look like this. Now, this is on my back. Imagine that on an 8-foot shaft. That would not be very pretty. And that's what those LCTs are protecting. That's what they're compensating for. And by reducing that, we're going to reduce stress on that vertical shaft. And by reducing stress on that vertical shaft, we're going to protect that shaft. Why is that going to become important? Because later on, we're actually going to talk about airspeed restrictions associated with this system not working, with this system failed in the retracted position. We'll talk about that here in a moment. Okay? Now, as we look at the components, this is the aft fixed link, aft strain gauge. There's the aft longitudinal cyclic trim actuator. The system's going to consist of the gauge up in the cockpit, which we already talked about. The strain gauge, or the fixed link strain gauge, is going to send a signal to what's called a signal conditioner unit. It's located in that forward left side of that forward pylon. That's where that signal is going to go to. That signal is then going to be sent to the aft pylon. In the back right-hand side of the aft pylon is going to be another black box. Only this is called a signal processor unit. Why? Because the aft strain gauge is going to send its signal directly into here. It's going to receive a signal from the forward strain gauge. It's going to process the two signals, and the worst case scenario is going to go down to the gauge in the cockpit. Now, you don't know if there's more stress on the forward than the aft or the aft and the forward. The system doesn't tell you that. It just shows you the worst case between the forward and the aft. Any questions about that? Okay. And we talked about the cruise guide test switch and where it's located. Limitations. Flight at or below 98% rotor RPM is prohibited if the LCTs are not working. Why? Because of what I just showed you and the stress that we put on that aft vertical shaft. And you can see why. Keeping in mind that the lower the rotor RPM, the more stress we're going to put on it. Now, the only other thing we have to highlight is that that 98 is included into the prohibited rotor RPM. 98 and below is prohibited. So we have to be at 99 or above. And normally we fly at what rotor RPM? Anybody done any? 100. We pretty much fly at 100 on a normal basis. So that's not a problem. Now, bull egg 2. Airspeed limitations. V&E will be determined by the use of charts in Chapter 5 on page 5-13. So what we're going to do now is we're going to go ahead and pull out our dash 10s and we're going to go look at that airspeed chart. Now, remember earlier we talked about we used to determine what the V&E was, but as long as we were in the green band, we could keep going. This is the airspeed that now has become, and you will notice in your chart, it's in Chapter 5, page 5-13. We have now changed the name of this chart. Okay, this chart used to be listed as your airspeed limit with an inoperative CGI, Cruise Guide Indicating System. In other words, if the cruise guide indicator wasn't working, that was the airspeed you had to maintain. But now this is the V&E for the aircraft, period. You cannot exceed this airspeed limit. Now, in using the chart, it gets a little bit confusing. Why? Because in using the chart, you're going to determine your airspeed limit based on either one of two situations. Either a structural limit or a blade compressibility limit. That's what we're determining. Now, the process for using the chart is identical in both situations, both with a load and without a load. What you're going to find out is when we get into performance planning, which is where we're primarily going to focus on this, gentlemen. We're not going to be spending a lot of time on this today. Because during PPC, we got 6 hours. And this is going to be reincorporated into that. Okay? So we'll talk about the basic uses of this chart so you can see what we're talking about. Okay? Now, it's going to be based on FAT, pressure altitude, and the gross weight of the aircraft. Those are always going to factor in. So what we're going to do is we're going to enter the top chart. And the top chart, the first thing we're going to enter is at the FAT. For an example today, we're going to use plus 15. And then you're going to come over to the pressure altitude in which we're going to want to fly. We're going to use 2,000 feet. Now, the average weight of these aircrafts is between 31 and 32,000 pounds with just the crew and a full bag of gas. and an empty fuselage. So we're going to base a lot of our information based on that today. Tomorrow, when we do performance planning, or excuse me, the day after when we start doing performance planning, we will base it on a empty aircraft and a full loaded aircraft so that you can see what it looks like. Now, why are we basing it on 32,000 pounds today? If you come down, you're going to notice 32,000 is way to the right of that chart. Agreed? So where you're going to stop is at that hard line that you're going to intersect. Okay? And then from that hard line, you're going to come and read over to the left. And that airspeed should be approximately 160 what?
265.
164, 165? I agree with that. Now, here's what we're going to do with that number, gentlemen. We are just going to write it down. Fair enough? Because we don't know if that's going to be our airspeed limit yet. The first thing we need to understand is what limit is that? That is going to be your structural limit. We tracking? We good? So now we have to do a blade compressibility limit. So we're going to go back up to the top chart, top left-hand side. We're going to enter it plus 15 again. We're going to come back over to 2,000. But now we're going to come back down to the dotted lines going across that chart to plus 15 again. Everyone see that? And then we're going to read to the left, and we're going to come up with what? What? 154? Give or take a little bit? Now what are we going to do with that number? We're going to write it down. Why? Because what has not factored into that process yet? We entered at the FAT, we came over to the pressure altitude, we came back down to the FAT. No weight. So if you look at the top right-hand corner, you have a chart that is now going to allow you to factor in weight. And what you're going to do is you're going to enter in that chart at at 32,000 pounds. You're going to come over to that hard line, and you're going to read down, and you're going to come up with a whopping what? 6, 5.5, 6. So we're just going to put a 6 there, and now we're going to add those together. Why am I adding those? Because I had a plus 15. What if I had a negative 15? Then I would have ended up subtracting that. And that's where it tells you you're either going to add that number or subtract that number based on are we at a positive FAT or a negative FAT. Any questions about that? But in this case, we're just going to simply add it, and we're going to come up with a whopping 160 knots. Tracking? Now, what is this airspeed limit based off of? Blade compressibility. And if you ever get confused, if you look at the bottom left-hand chart, or bottom chart left-hand side, you will see that it will have your hard lines are your structural limit, your dotted lines are your blade compressibility limits. Any questions about that? Now, are we done yet? No, because now I have two airspeeds. Which one am I going to use? What makes sense? The lowest of those two numbers. So we're going to use 160 knots. Now, what has that become to us? Our V&E. What was it before? Before, that was the only an airspeed limit that we used if the CGI, the cruise guide indicating system, wasn't functioning properly. Now that has become our V&E, and you will see why later. During performance planning, we will actually show you pictures of structural cracks caused by exceeding the limits and pushing the envelope as far as the cruise guide indicating system is concerned. Any questions about that? Okay. So that's bullet 2. Bullet 3, airspeed limit, V&E with the retracted LCTs will be determined by the use in the chart in chapter 5 on page 5-14. Now this chart's a lot easier to use. Why is this chart a lot easier to use? Because all you have to do is enter at the top box, left-hand side at the FAT. You come over to the pressure altitude, which hasn't changed, has it? And you're going to come down again to the weight of the aircraft. But you'll notice 32,000 pounds is way to the right of the chart. So we're going to stop where again? The hard line, which should be approximately what airspeed? 98, I concur. Now, why is that important? Again, this airspeed limit is only going to factor in when. So we understand, when is this airspeed limit going to be my factor? When the LCTs failed retracted. Meaning what? Meaning when you first put this aircraft or pulled this aircraft up to a hover, what happened is those LCTs retracted for the process of what? Negating that predetermined transmission tilt based on the mounting of the transmissions. Now, as a result of having that pre-tilted transmission, this aircraft has a natural tendency to want to fly or go forward. So you had two choices. They either had to give a system that compensated for that, or you would have had to pull in an unusual amount of aft cyclic to allow you to do your hover work. So what they did is, as part of the process, through those longitudinal cyclic trim actuators, they're going to come to the retracted position, leveling off your rotor system, allowing you to do hover work. But now, as you increase airspeed, what's going to happen is those LCTs are going to program to tilt forward to allow you to fly with a more level fuselage, and they're also going to be compensating for blade flapping. Fair enough? If they are failed retracted, we're going to get back into that what again? Remember how ugly that looked the first time? Does it look any better the second time? I don't think so. Okay? So that's where this airspeed becomes a major deal. Now, let's go ahead and nip it in the bud. If those LCTs fail forward, what is my emergency procedure? Anybody studying already? It's going to say airspeed adjust. Now, as soon as I read airspeed adjust, what is my mindset? Huh?
It's always slowing.
It's always slowing down. That's a natural tendency. Agreed? But if they're failed retracted, the only thing I want to adjust my airspeed to do is what?
Stay above that minimum.
It's maintain where they're stuck at. And everybody gets all bent around the axle about that one. All you're doing is, if they're stuck at 140 knots, maintain 140 knots. No harm, no foul. Good? This emergency procedure and that airspeed limit only factors in if they're stuck in that retracted position. That's the only time that's the airspeed limit. But now, this is also a good point of interest in the fact that if I operate on a single AFCS, my airspeed limitation is what? Okay, and that's where everybody stops. 100 knots, but that's not what it says, right? It says 100 knots or V&E, whichever is slower. And a lot of people tend to forget about the V&E or whichever slower portion. We get stuck on that 100 knots. This is a good example of when my V&E may be less than 100 knots. Questions? Concerns? Moans, groans, gripes, complaints?
Is there any, like, just general rule of thumb because of the ability for this aircraft's gross weight to change all the time? I mean, as far as, I know we're probably covering PPCs, I'm just trying to think of it in my mind. I mean, because you just gave us an example of we're operating at 32,000 pounds, there's 160. I mean, is there some simple method, or does it have to be recomputed every time, you know? you
Well,
drop?
under performance planning, basically what you're going to do is you're going to base your information off of, at the time of takeoff, what your pressure, altitude, and FAT is. And then you're going to base it off the max conditions that you're going to encounter throughout your flight. For performance planning, that's all we're going to do. Okay? We will also do it for both envelopes. An empty aircraft and a fully, whatever the load is going to be for the day. So you'll have both parameters on that card.
Yeah, I just wonder if there was something like for every additional 1,000 pounds, you reduce that airspeed by.
No, sir, there's no such thing. There's no such thing. And you also have to remember that this is a new way of using this chart. Okay? Prior to this, the only thing we used this chart for was if our LCTs, or excuse me, if our cruise guide indicator stopped working. Other than that, we could fly at any airspeed up to what? 170 knots, which is why that write-up says of 170 knots. But now you'll find out that although we're capable of flying 170 knots, we can't actually go to it depending on our pressure altitude that we're going to be operating at. So what do you think they're experiencing in Afghanistan? Okay. Not are they experiencing the fact that they're having to fly slower, but they're also experiencing that they can't carry as much gross weight as we normally do, depending on the pressure altitude that they're operating at, which is a major deal for us. You know, normally you call, we haul. Okay? Reality is, and you're going to get excited about it, when we talk about performance planning starting next week, you're going to be amazed by the weight that we can carry single engine. And you will actually see that figure. And it will actually get you very excited about this aircraft. Okay? Anything else? Any questions whatsoever? Okay. For the last almost 3 hours, we've been talking about the flight instruments on the CH-47D. And pretty much all we've been covering is differences on how these flight instruments react with the systems on the aircraft. Are there any questions about anything we covered pertaining to the entire system? If not, then gentlemen, have a wonderful day.